Let me begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Thank you again for these students. Just ask you'd guide our steps today, help us to understand a little bit more about how to graph, and I just pray that you'd encourage the students, if they're not doing as well as they'd like to, just to help them to take the steps they need to do better, Lord. In your name I pray. Amen. Okay, so you can clean this board off a little bit here. Any questions while I'm cleaning? So let me give you a thumbnail sketch of what we're about to do here. What I'm about to do is to share with you guys standard examples of graphs. All right, so there's a certain set of examples that everybody should know without thinking. You should just have them memorized, basically. And when I say know them, I mean have a general idea of their shape so that you could make a quick sketch of it without really worrying too much about particular values. You want to know the general shape of it, anticipate, basically what it looks like. On the other side of things, of course, you also want to be able to make careful graphs where attention to detail is given, right? So, and how do we make a careful graph where attention to detail is given? Well, there are a few different ways. Of course, we can use technology to do it, but the point of this course is not that. So we are studying graphing in here mostly without technology, and for the reason for that is to gain a better understanding of how functions work and also the interplay between graphing and algebra itself. So it doesn't involve technology too much, although of course your homework is electronic, so annoyingly that is the case. But you really do need to, more in this part of the course than ever before, make sure you're working your homework out on paper in addition to whatever you're putting in the computer. Because it's really, graphing is something that we're going to do on paper, and I will expect you to draw graphs on the next test. So anyway, let's just get straight into it unless there's a question. So I'll start with a example. And so my first example will be forming a graph with a table of values. All right, and so I'm going to make up an example. Okay, so here's our example. We're going to graph f of x. And because we need work on this, I'm going to use what's called a case-wise definition. All right. So case-wise definition means you define the formula in cases. So what I'm going to do is something like, I don't know, thinking -3 minus x, and that's for x less than 2. All right, and then let's say x squared plus 1 for x greater than or equal to 2. So the way this works is there's two different formulas, right? And which formula you use depends on what case you're in. Now I want to show you how to make a graph. And so the way I'm describing right now is pretty much the most boring possible way to make the graph. But it is a good way. I mean, it's sort of the most basic rudimentary way to form a graph, which is just to plug in a bunch of points and find the points on the graph and then connect the dots. Yep.
Are we going to operate where y is going to be the input and x is going to be the output?
No, for us, I will exclusively focus on x being the input and y being the output. For now, there is a place where I talk about the opposite, but not today. So default here, functions are functions of x. That's just like an assumption in this course, yeah. But you're right, you could think about functions of y just the same. You could do that. So let me just pick some numbers, all right, to get us started here. So we could look at, say, -2, -1, 0, 1, 2, 3, and 4. That ought to be plenty. And so in each one of these cases, I'm going to evaluate the function. All right? So what is f of -2? Let me use a different color. What is f of -2? I heard -5. Now how do you know that? I'm not. So it's -3 minus a -2, and I see I have made this too small. My bad. So that is equal to? You said -1? Okay. And let me add yet another column. I mean, this column is kind of, you know, here's the point on the graph. So from the first row, the graph I'm going to draw, it should have the point -2, comma -1. That's one of the points on the graph, right? Now let's calculate f of -1. F of -1, which case am I in? -1 is less than 2, right? So I still use the -3 minus x. So I do -3 minus a -1, which of course is -2, right? So what point do I get on the graph? I get a -1, -2, all right? Now f of 0, what's f of 0 equal to? -3 minus 0, right? So it's -3. What point on the graph do I get? I get the point 0, comma -3. Recognize that's the y-intercept of the graph, right? That's where it crosses the y-axis when x is equal to 0. F of 1. I'm still in the first case. This is kind of boring in that regard. I get -3 minus 1, which is, of course, -4. The point on the graph that it's going to give me is 1, comma -4.
Isn't it -2 because it's... Oh, never mind.
It's okay. F of 2. F of 2. Oh, now hold on a second. Hold on a second. F of 2. What case are we in?
X squared plus 1.
Tell you what, I'm going to color code this thing. So everything in red has been this case, right? The other one, the remaining ones, are in the other case, this guy, right? So f of 2 is 2 squared plus 1, which is 4 plus 1, which is 5, right? F of 3 is 3 squared plus 1, which is 9 plus 1, which is 10. F of 4 is 4 squared plus 1, which is 16 plus 1, which is 17. Lo and behold, the last 3 points are in the other case of the function. And so we have 2, 5, 3, 10, and 4, 17. So how do you make a graph? Like, what, if you're making graphs for this course and also for your science courses, what should you think about when you're making a graph? Like, do you have to use 1 division equals 1 unit? I mean, you don't have to unless it's forced upon you. Like, I might have and that probably will be the case on your test. I might have like a graph paper written on the paper and say graph on this, assuming that 1 unit is 1 division. I might even have the numbers on there already. That's just because then my grading is like way easier because they all have to look the same, right? Because if you choose different scales, the graph can look really, really different, right? So a lot of us have the bad habit of just making whatever kind of scale without thinking and then plotting the graph, right? If you do that, what happens a lot of times is that the interesting part is like one tiny little corner of the graph, right? And you have a bunch of blank wasted space. So really, once you have the data that you're going to graph, it's important to think about what's a good choice of range for the x values and for the y values, right? So the x values, well, I've made them go from -2 to 4, right? How about the y values? They're going from ranging from -1 to -2 to -3 to -4 all the way up to 17, right? So it seems to me if I do something like, oh, I don't know, -10 to 20, that's going to cover everything generously, right? So let me do that. Let's see here. So I'll make this, I'm going to use my handy dandy hand measure, -10, 10. Apparently, there was a time when math people sometimes were tasked teaching algebra in like a music classroom, and at the time we had chalkboards, so there were professors who had to like teach math on top of like the you know, the bass and treble clef. Can you imagine that? But it'd be really useful right now. You'd have the lines to graph with, you know. But all right, so I'm gonna make this 4. -4 halfway points I can usually do. So I don't have to put all the numbers in. I just need to put enough numbers in that it gives me a sense of scale, right? So if I have my stuff together here, I will bring a handout for a future class. And so there actually will be some honest to goodness in-class participation here pretty soon, because I'm going to have a thing for you to fill out and to I might not make you turn it in. I might let you keep it, actually. But probably, hopefully for next class, I think that would be good. Anyway, thinking ahead. So here, I plot the points, right? Where's -2, -1? -2, so -2 is the x, -1 is the y, right? So annoyingly, that's about right where I drew the number -2. See that? So it's about right here. That's my first point. -2, -1. Then -1, -2 is round about here, right? 0 -3 is about there. Okay. 1, -4 is about here, right? I was wondering what this thing was for. I figured it out. I gotta put it the other way. I don't know, they really shouldn't have this bar on here. It makes it inconvenient. So if you do like this, I think that's what it's for. I'm not sure. That's my theory. I was in Alabama the last 2 years, so I'm not really sure, but all right, there we go. Apparently it's a line, right? The only other thing I could figure is you could draw a mustache on this and stand behind it, you know, or whatever. So all the way over to 2. And now 2, there's a circle here, right? Because this case doesn't include 2, right? But it goes this way. Now, up till now, I have not given you any graph on a quiz or a test that had the arrows at the end of it. And my examples in class didn't have that either. But this arrow at the end of it means it goes on to -infinity, right? Okay, just saying. And then, let's see, we pick up at 2. At 2, we're at 2, 5. They're rowdy today, aren't they? Let's see here. I'm going to have to go out there and give them the what for. Let's see here. So we're at 5 at 2, and then at 3, we output a 10. And then at 4, we're outputting 17. Right? So up and up and up it goes. So what we're looking at then, of course, is the graph, right? This is y equals f of x. Right? And if you have that graph, you can answer questions like, what's the domain? What's the range? Well, the domain is everything, because it has a formula for x less than 2. It has a formula for x greater than or equal to 2. The domain is everything. What's the range? range equals, what was that? You said -5 to infinity. I like that, but is -5 included or excluded? Excluded, right? Open circle. So, what's that? A lot of you are still working on this. Okay, this is on the next, so it was on test 1, it's going to be on test 2. Many of you are still very, very shaky on understanding domain and range. And I think a good part of that is you still haven't really understood what the interval notation means. I'm just guessing. I really don't know for sure, but people need to work on this. How do you find the domain and range from the graph? The good news is there's a bunch of homework problems on it in the next homework, so that should help, I suppose. All right, so this method of graphing, what time is it? 2:28, when's class start? Like 2:10, right? So it took me 15 minutes to do this. It's pretty slow, isn't it? Yeah. So this is not a good way to do graphs that could be done in a quicker way, right? Plugging in points and making careful graphs like this it's very laborious, right? So we want a better method, and the better method is basically for many graphs that are related to a standard set of sort of canonical examples, we can take that standard list of examples and just shift them around, and that's a method of graphing. So let's talk about that. I'm going to erase. Now, of course, what's the other way you guys, you use a graphing calculator to do this kind of thing too, right? Sort of. But I don't know, how many of you can do this in the graphing calculator? Cases? Maybe, maybe not. I mean, I'm pretty sure that the TI-84, maybe the 80, I mean, there surely must be a case-wise defined grapher in the Texas Instruments calculator, but good luck finding it. But I'm sure some people spend a lot of time and energy teaching that to students in high school. I don't think that's a wise use of time, honestly. So we want to learn how to graph by hand because it strengthens our understanding of what the functions are. And it actually will strengthen, so like it feeds, it's mutually beneficial. Everything you've learned about factoring so far will now soon feed into what you know about graphing. They tie together. You're going to see that there's a synthesis of these ideas. But anyway, we're not quite there yet. We need to look at the standard examples first. So I'm just going to rattle off a list and show you what they look like without like a lot of proof or anything like that, okay? So first of all, you've got y equals mx plus b, right? Second of all, you've got y equals ax squared plus bx plus c, you know? You got things like y equals ax cubed plus bx squared plus cx plus d. So what are we looking at here? The first one's a what? This is a line, right? Parabola. And for lack of a better name, I call this a cubic. What do they look like? Grossly speaking. Like not fussing about the details. Like what is their basic shape? Line we know, right? So I'm going to draw 6 pictures. For cases, first of all, case 1, second of all, case 2, third of all, case 3. Here's the pictures. Like this, like that, like this, like that, like this, like that. So this is the large, this is what it looks like large scale. These are the basic behaviors. Now, can you guys help me out? I'm saying that there's these different cases. There's like subcases of number 1, number 2, and number 3. And almost got it. So you guys help me out. This is what we talked about this already, right? This is slope positive, right? M greater than 0. This is slope negative, right? M less than 0. How about this over here? This means that the leading coefficient A is positive, right? If the A is positive, it opens up, right? If the A is negative, the parabola does what? It opens down, right? And then cubics, they either look like a snake that does like this, right? So the general direction is like increasing, so to speak. So this would be A greater than 0, and this guy down here would be A less than 0. So, you know, where exactly is the y-intercept, right? Where is the x-intercept of these things? I don't know. I'm not interested in that at the moment. What I want you to get across to you is that if I've got this, this, or this, they look generically like these cases, provided we understand the leading coefficient, positive or negative. This gives us the big picture of them. Now your book in the WebAssign, they've got some kind of funky arrow pictures, like there's an arrow like this, and there's an arrow like this, and they're like separated. So like basically what your book does, and I'm going to have to murder my pictures here. I hate to do it. But if you could just imagine like erasing the middle, that's kind of their pictures in the WebAssign. I mean, excuse me, my labs. Let me not talk about the homework. This is what they look like if you could zoom out. Now, to figure out the x-intercepts and the y-intercepts, we're going to have to do a more careful analysis of a particular formula, right? And we'll get back to that. But let's continue on with the standard examples. So actually, truth be told, the 3 things I just gave you, I wouldn't really, that's not actually what I'm talking about with standard examples. My real standard examples are starting over here. They're more simple than this. Like number 4 would be y equals x squared. Number 5 would be y equals x cubed. Number 6 would be y equals, x to the 4th. Number 7 would be y equals x to the power 5. I think that's enough. So what do those look like? It's like y equals x squared. Let me do them down here. So y equals x squared, if we want to understand it just, quickly, it just looks like this, right? Basically, this is y equals x squared. It's a parabola, goes through the origin, opens up like that, right? What's y equals x to the 4th? So y equals x to the 4th looks kind of the same. The difference is, if you track like this point right here, if I did it right, if we're at the halfway point, if this was actually the halfway point, trying. So what's 1/2 squared? 1/2 squared is a quarter, right? So the y equals x squared graph goes through a quarter at a half, right? Where does the y equals x to the 4th graph go at a half or minus a half? If we do 1/2 into x to the 4th, we get a 16th. So it's down here. It's much lower, right? And then on the other hand, it's up here. So the y equals x to the 4th, if I draw it on the same picture, it kind of looks sort of like this. I really need to get a computer out to do this justice, honestly, folks. And I probably will get the computer out next week and show you some things, yeah. Because there's something better than a graphing calculator. If you're going to use technology, we should be smart about it. There's a website called desmos.com, which is extremely useful especially if you have another class in your sciences or whatever where you want to understand how a function looks and analyze it. Desmos.com. It's a free graphing software app online. Very useful. Anyway, so the x to the fourth is like more steep, and it's more shallow. It's like closer to the x-axis before plus or minus 1, but then it gets even steeper. If you look at like x to the 10th, like if you look at y equals x to the 10th, it would look kind of like this, roughly speaking. And here's like minus 1 and 1. It just essentially looks like goalposts, right? So as you get higher and higher powers, this kind of like balloons, it just keeps being more and more steep when you get past 1, something like that. Anyway, those are even powers. So grossly speaking, the big picture here is that if I have x to an even power, it looks basically like this. This is y equals x to the 2n. Any even power, roughly speaking, looks like that. The odd powers, on the other hand, right? X cubed looks like this. All right? And if I was being so foolish as to try to plot both on 1, if this is like 1 and this is like minus 1, then I've just done y equals x to the 3rd power. What does y equal x to the 5th power look like? It's like it's closer to the x-axis before here, and then it's above or below over here like that. So, crudely speaking, an odd power looks roughly like these. Of course, what's the first odd power? Just y equals x, right? I haven't even drawn that, but you can kind of see how that fits into the story, right? Y equals x is just the line. Same kind of pattern. Notice that, have we talked about this before? I don't know if we have or not. These are what are called even functions, right? Even function has f of minus x equals to f of x, right? Odd function has f of minus x equal to minus f of x. So if you look at the graphs of y equals x to an even power, it has this symmetry, right? Whatever's to the left of the axis, the y-axis, it just mirrors over and gives you the right half, and vice versa, right? If I give you the right half of an even graph, you can just flip it over the y-axis and get the left half. With an odd graph, whatever you have on the right, you flip over, and you have to reflect it down to get on the left. So these are examples of odd functions. These are examples of even functions graphs, right? And of course, there are also functions which are neither even nor odd. Like my example 1 today it wasn't even or odd. It was something else entirely, okay? Are we good? Okay, so this is the start of it. Now let's get to the more interesting standard examples. 8, well, let me do it over here. Oh, it's okay, I'll get it. I flipped the viewfinder so I can, but you'll have to remind me to move it back, otherwise I'll start writing over here and projecting over. Anyway, let's see here, 8. We could have y equals, how about this, the square root of x. That graph, what does it look like? Yeah, I saw it. So it looks like this, right? Now, how does that relate to other things we have on the board? Is it related to anything? It is, right? So if you take this and you square it, what do you get? We get y squared equals to the square root of x squared. Now, some of you on the test are putting plus or minus when you square the square root of something. No. No plus minus here. It's just x. So the square root of x squared is just x again. And so what we have is x equals to y squared. So if you think about this logically, right, it's going to be the same picture that we had for y equals x squared with the roles of x and y flip-flopped, right? So if you graph this thing, you don't get just this, you also get all these points down here, right? But what are these points down here? These are y equals minus the square root of x, right? So like y equals minus square root of x together with y equals square root of x up here, together those give you x equals y squared, right? Which is not, this is not the graph of a function, right? Because if you have both of these together, you fail the vertical line test. But just the upper half is the square root function. Okay, so what's dotted is not part of the example technically. What's the domain of this one? It's 0 to infinity, right? What was the domain of my other examples? 4, 5, 6, 7, actually 1, 2, 3, 4. All of the examples up to now, what's the domain been? Infinity both ways, right? These are polynomials, so the domain's everything. Now, just non-negative reals, yeah? Now, by the way, so let me just make a remark. Y equals to the square root, we'll put a 2n up here of x, which is x to the 1 over 2n, looks similar. So these are even root functions. So-called even root functions. Any even root function has a domain which is the non-negative reals. Yeah. What about odd root functions? How about those? What about y equals the cube root of x? What's that look like? So if you want to think about it, this, if we cube it, we get y cubed equals to x, right? So you can understand this shape by taking the cubic function, right, and just flipping it x for y. And if you do that, what you get is this contraption. So it keeps going up, and it keeps going down and down. There are more interesting math classes. You find.
I just gotta leave a little bit early.
Oh, wait a minute, you're not CFA. Wait a minute, you're not CFA.
I'm not.
Hey,
I just had like I had to go to something.
you have to go to something. I was going to get back tests at the end.
I can take it next class.
Okay.
Thank you so much.
If you want somebody to pick it up, they can.
That's okay.
Okay. Okay. I understand. I'm not important. I get it. Let's see here. Wait a minute. That was for when he was here. Oh man, I always think of whatever to say to him when they leave. If you ever leave early, just watch the video for whatever snide thing I say after you leave. You know, I don't edit them out unless they need to be edited out. I mean, let's face it. You never know what needs to be edited out. If you think about YouTube 10 years from now, anything I say could be politically incorrect. I don't know. Who knows? Political correctness is a moving target. We don't even talk about political correctness anymore anyway, do we? They have a new term for it. Authentic speech or something, is that what it's called? Authentic speech. Your speech should be authentic. I saw on Twitter, they only are approving of authentic speech about elections. What on earth does that mean? Who decides what's authentic? Good grief. Anyway, y equals the cube root of x. This is what that looks like? What's the domain of this guy? Right. And guess what? Remark. If you have y equals to the 2n plus 1th root of x, which is x to the 1 divided by 2n plus 1, looks similar. So any odd root function looks pretty much the same as this. All right. Oh, you know what? I just realized what I left out of the earlier class. Curses. Here's another one. Y equals absolute value of x, right? That's a standard example. What's that look like? It's a what? It's a v, right? So we like to mess with this one. There you go, that's y equals absolute value of x. Number 11, the reciprocal function, y equals 1 over x. The reciprocal function looks like this. So it has a horizontal asymptote of y equals to 0. It has a vertical asymptote of x equals to 0. If you don't mind, so I'm using an abbreviation, horizontal asymptote, HA, horizontal asymptote, and let me just graphically indicate that. The horizontal asymptote is actually the x-axis itself, y equals 0. Okay? The vertical asymptote is the y-axis in this case. So it's this one. Okay? So this reciprocal function has both a horizontal asymptote and a vertical asymptote. Does anybody know what this shape of this graph is, by the way? In terms of classical geometry? In terms of classical geometry, the parabola is the set of points which are equidistant from a focal point and the directrix, right? So you have a focal point, you have a directrix, you take the locus of all points, where the distance from the directrix to the focal point is equal. That gives you what's called a parabola. Optical, you can have a parabolic lens based on this idea. This is the set of points where the difference between two fixed focal points is held constant. This is what's called a hyperbola. There's also something called an ellipse, which we might get to later, but circle being the most famous example of those. There's also what I call, and this is, this one I called the reciprocal graph. I didn't write it down, let me write it down. Reciprocal graph. You see why I call it the reciprocal graph? It's because it's reciprocal of x. I mean, it's not fancy. My label here is a little bit more surprising. I call this the volcano because it looks like a volcano. So I don't think that's like standard mathematical terminology, but I'm certainly not the first person who said it, and I don't think I'll be the last because it looks like a volcano. So, like this. Right. There's y equals 1 over x squared. Okay. And this also has a horizontal asymptote of 0, y equals 0, and it also has a vertical asymptote of 0. So this shares the same horizontal and vertical asymptote as example 11. All right. All my standard examples, we could have verified what I said is true by doing what? Going back to example 1, spending 15 minutes to plot a table of points, connect the dots, say, oh, that's the shape, right? But let's agree that we know these shapes. All right, now that we know them, we can play games with them. So the next lecture is going to be about how we move these things around to make new graphs. So yeah, we have enough time for one of those, maybe. And then, so that's, let me do words, to give you a view ahead. The next thing we're going to do is to move these standard examples around using transformations to make new graphs. That is by far one of the fastest ways to create graphs. All right? Then once we get done with that, then we will shift gears and we will look at how does polynomial factoring feed into the question of graphing. So we'll take a really in-depth look at, how to get zeros from factoring and the factor theorem and all that. So we'll do a lot more factoring again. So here's example 2. Suppose you want to graph y equals x squared plus 1. All right? So the way to think through this is pretty simple. You think, okay, well, I know my standard example. This is y equals x squared, right? And then shift 1 up. So the 0, 0 moves up to 1, 0, and there you go. That's the graph. So if we take the value of the function and we just add a number to it, it shifts it up. like that. In contrast, example 2, if I take y is equal to, say, x minus 1 squared, right? What this is the same basic idea as example, oh, sorry, 3. My bad. Same idea as example 2, but this one, we do what? We shift 1 right. So if you replace the x with x minus 1, that moves 1 to the right. So we take this point and we move it over to here. Right. So replacing x with x minus 1 shifts 1 to the right. Here's one more example. We'll do tons of these next class, all right? But another example for today, if we look at y equals to apps value of x plus 2 plus 3, how would you do that? This is a two-stepper. So we start with apps value of x, right? Adding 2, what that does, that's shifting 2 to the left. Shift left 2. This is y equals apps value of x plus 2. So if we replace x with x plus 2, it shifts 2 to the left. And then finishing blow, up 3, right? So I take this point, which was 2, 0, and that shifts up to 2, 3, and like so. So there you go. This point would be at 2, 3. This, what I just did in 30 seconds, now you might not be comfortable with it yet, and that's okay. We're just learning it together, you know. You have to do a bunch of problems before you get comfortable with it. But once you get comfortable with this, if you know your standard list of examples, it is so much faster to create a graph like this than the method I used in example 1, right? Because you start with your standard example and you shift it appropriately to get the final graph. But anyway, I will stop there. Now let me talk about the test. So